So a solution can be composed of any combination of phases or states, solid, liquid, gas. In an aqueous solution, aqueous tells us water is the solvent. If water is not the solvent, it's not an aqueous solution. In an aqueous solution, that solute may be a gas, a liquid, or a solid. And here we have some examples of solutions. You can have a solution in the gas phase where both the solute and the solvent are gases. The air that we're breathing right now is a mixture of gases. It is a solution. Liquid solutions we're more familiar with, something like club soda or, Diet Dr. Pepper. We have a gas, carbon dioxide, dissolved in water. So the solute is a gas. We can have liquids mixed together. Most alcoholic drinks are liquid-liquid solutions. The alcohol in those solutions is, the ethanol is the solute, and water is the solvent. And those are both liquids, and they mix together and form a homogeneous mixture. Solids can also dissolve in liquids, like seawater, salt in water, or you can take a teaspoon of sugar and stir it into water. It dissolves. That's a solid being dissolved in a liquid. You can also have mixtures of 2 or more solids. Like, how the heck do you get 2 solids to mix together? Well, you kind of have to heat them up and do stuff to them. But alloys, such as brass, pewter, even stainless steel, are all alloys. They're solid mixtures of different components. So what kinds of things will dissolve in each other? Any given solvent will not dissolve everything. So water is considered the universal solvent, but not everything dissolves in water, which is good, because if everything dissolved in water, we couldn't have boats or anything. The whole planet would dissolve, right? You can take all of these things to ridiculousness. Just made up another stupid word. So what we call solubility, solubility tells us the amount of substance that will dissolve in a particular amount of solvent. Now, a lot of times that amount of solvent is 100 grams. So we might say the solubility is 22 grams per 100 grams of water. You need to specify both the amount of solute and the amount of the solvent. So solubility is depending on that tendency towards mixing. And the types of intermolecular forces present in the solute and the solvent are going to have a big effect on whether these things will mix or not. So many physical systems tend towards lower potential energy. It's a driving force of nature. Forming a solution, though, does not necessarily lower the potential energy of the particles. So if we think of 2 ideal gases, so here we have neon and here we have argon, and we take the barrier away, and we know what's going to happen is that these particles, according to kinetic molecular theory, are bouncing around till they run into something. So this one might go over here, and then if the barrier's gone, it's going to come over here. The particles are going to mix. But the mixing does not lower their potential energy. It doesn't change their potential energy at all. So why do they mix if it isn't energy? There must be something that causes them to do that. And that something is entropy. So entropy could be described as a measure of energy randomization or energy dispersal in a system. So those 2 ideal gases mixing, the kinetic energy of each gas becomes more spread out, more dispersed, because now it's occupying a larger volume. And so entropy has increased. Entropy can also be thought of a tendency towards disorder. So, my house is a living testament to the power of entropy. Yours is probably too. Because what happens if you don't put any energy into keeping the house tidy? It becomes a mess unbelievably fast, right? There's socks and dog hair and dirty dishes, and it's just like they come out of nowhere. Because it takes energy to put those things back where they came from. And so entropy is like, playing 52-card pickup with a deck of playing cards. You throw them on the floor, they don't land in piles. The leaves falling from the trees right now were ordered when they were on the tree, right? They were in patterns. When they fall off, they scatter all over the place, right? That's energy dispersal. Their energy is spread out over a greater volume. So substances mix because of this tendency for energy to spread out whenever it is not restrained from doing so. Entropy also explains the transfer of thermal energy from hot objects to cold ones. We've talked about that. We didn't explain why that happens. You put an ice cube in a hot cup of coffee. Why does the energy move from the hot coffee into the cold ice cube? Because that causes its energy to spread out into a larger volume. Its entropy increases. Any questions? So intermolecular forces can promote the formation of a solution or they can prevent it. And we've recently studied all these forces. And this comes down to like dissolves like. We mentioned that earlier. So here we have heptane and pentane. These are both alkanes, hydrocarbons, just carbon and hydrogen. They're very nonpolar. So they have dispersion forces because everything has dispersion forces. But dispersion forces are the strongest force for each of them, and so these are going to mix together very nicely. Acetone and chloroform are polar compounds. They have dipole-dipole forces. Those forces are similar in nature and similar in strength, and so those will mix together very nicely. Ethanol and water both have hydrogen bonding as their strongest intermolecular force. Again, similar type, similar strength, and so those mix together very well. But heptane will not mix with water because the water molecules are very attracted to each other by their very strong hydrogen bonding, and the heptane molecules can't compete, and so they get squeezed out. The ion dipole force is what allows things like sodium ions and chloride ions to dissolve in water. We have the interaction between dipoles of the water and the actual ions of the solute. So we've got intermolecular forces in three different relationships. We've got between the solvent particles, we've got interactions between the solute particles, and then we have interactions between the solvent and the solute. So like dissolves like. If the intermolecular forces of the solute and the solvent are similar, the solution will probably form. Miscible is the word we use to describe two liquids that are soluble in all proportions. So alcohol and water are miscible. You can take a glass of water and put 2 drops of alcohol in it, and it'll mix up just fine. You could take a glass of neat alcohol and put 2 drops of water in it, and that will mix up just fine as well. You can't do that with everything, but it does work with liquids that are soluble in each other. Now, some of them you can dissolve a little bit, but not, there's a limit. But a miscible liquid, they'll dissolve in any proportions. They're completely soluble. Miscible's a weird word. It kind of sounds like mixable, and that's what it means. They're mixable. So we're looking at comparing the strength of the interactions in these 3 different relationships. So if the interactions between the solvent and the solute are strong relative to the solvent-solvent and the solute-solute interactions, then a solution will form. So this is like two groups of people perhaps I'm debating whether to modify my analogy or not. Well, let's do it this way. Yeah, I'm going to take the same one and tweak it a little bit. Okay, so I'm of Swedish descent. My husband is of Japanese descent. And so I can talk about those two ethnic groups without being racist, right? Because I'm talking about myself and my husband. So imagine a room with a group of Swedish women who only speak Swedish and a group of Japanese men who only speak Japanese. Is there likely to be much mingling, socializing? Well, the women are going to speak Swedish to each other and the men are going to speak Japanese to each other, right? Because the interactions between the men speaking Japanese with each other are strong. It's difficult for them to communicate with the Swedish women because they don't speak the same language. So that's the effect of the similar type of interactions. So you can think of it as a language that these particles are speaking. So that would be something like this, where the solvent-solvent and the solute-solute interactions are stronger than those between the solvent and the solute. So the interactions of the solute, let's say the women are the solute, they're speaking Swedish to each other. Those interactions are stronger than what they have with the Japanese men. And so it's not going to mix well. Depending on how much greater that is, the solution may or may not form. It depends on the relative disparity. Now, what if all those people speak English as well as their own languages? Now you're going to have some mingling, right? Because you've got men and women, and so there's this attraction between the men and the women that's maybe more important than, talking to the other guys from the same country. I don't know that, I'm not sure that I need to work on this analogy. Anyway. So there the solvent-solute interactions are going to be strong, perhaps even stronger than the interactions between, say, the Japanese men with each other and the Swedish women with each other. Now the Japanese men and the Swedish women, that interaction is stronger because you've got, gender differences going on there, and so a solution's going to form. If those interactions are relatively the same, a solution will also form. Does that make any sense? If the solvent-solute interactions are a lot weaker than solvent-solvent and solute-solute, the gain in entropy, the spreading out of energy, doesn't make up for the energy loss of those stronger interactions, and the solution will not form. So we've got these interactions between the two different substances, between the particles of the solvent with the solvent, the solute with the solute. In order for them to mix, those interactions need to be broken and new ones need to be formed. If you lose a little bit of energy in forming the new interactions, it might be made up for by the increase in entropy. But if you lose a lot of energy because of breaking those original interactions, it's not going to be made up by the entropy and it won't form a solution. Okay, so that's the long, complicated explanation. It comes down to, can we answer questions like this? Determine whether each compound is soluble in hexane. So we need to know what hexane is. So this name, we've got hex, which is a numerical prefix, and ane, we learned a while ago that those are alkanes, they're just carbons and hydrogens. And hex means 6, so hexane would have 6 carbons. So it'll be C6 and a bunch of H's. It doesn't matter if you know exactly how many H's there are. It happens to be 14. So hexane, is this polar or nonpolar? It's nonpolar because carbon-hydrogen bonds are nonpolar, and so this whole molecule is going to be nonpolar. There's no lone pairs on it. Just remember that carbon-hydrogen compounds are nonpolar. So then we're looking at how this is going to mix with water. Is water polar or nonpolar? It's polar. And so then we have to ask ourselves, well, what kind of intermolecular forces does it have? It's got hydrogen bonding. It also has dipole-dipole forces and dispersion forces, but we usually compare the strongest one, okay? So this has hydrogen bonding. This one, being nonpolar, only has dispersion forces. Are those going to mix together? Are their interactions similar? No. Hydrogen bonding is much stronger. These guys are really tight with each other. And the hexane comes in, it's speaking a different language. These guys are so involved with each other, it's like a clique. They're just not going to let any outsiders in. And so the hexane is excluded. So water will not be soluble in hexane. If here we're talking about putting the water into the hexane. So the water comes into the hexane and it looks around and it just clumps up with the other water molecules. You can see this, if you try to mix it up, it'll actually form little droplets and then they'll eventually all get back together again. So no mixing. We'll just say not. How about ammonia and hexane? What's the strongest intermolecular force in ammonia? It's hydrogen bonding. So here is the Lewis structure. So this is a polar molecule. Remember, a shortcut for determining polarity, if it has a lone pair on the central atom, is probably polar. These bonds are also polar, and so this is going to be a polar molecule, and it's got nitrogen-hydrogen bonds. Remember ET phone home? Fluorine, oxygen, or nitrogen bonded to hydrogen. This also has hydrogen bonding. Is that going to be soluble in hexane? No. Here's propane. Polar or nonpolar? Nonpolar. So that's nonpolar, it's just carbons and hydrogens. So that has just dispersion forces. Propane speaks the same language as hexane. It speaks dispersion force. And so these guys are going to mix together. So yes, this will form a solution. It's soluble. How about hydrogen chloride? Polar or nonpolar? Polar. So this one, you've got hydrogen and chlorine, just two different elements. We're not going to use electronegativity tables on exams. I want you to just have this general idea of, is this polar or not? So here we've got two different elements. Most of the time, if it's two different elements, it's a polar bond. So two different elements, this is going to be polar. It doesn't have hydrogen bonding because it doesn't have fluorine, oxygen, or nitrogen, but it's polar, and so it's got dipole-dipole forces. And those dipole-dipole forces are stronger than dispersion forces, right? So is this going to form a solution? No. I'm at least getting some people shaking their heads and nodding, but mouthing words, but nobody's willing to say anything out loud. That's okay. I was that student that sat in the back and took notes and paid attention and never, ever asked a question. And I turned out okay. There's hope for you guys. Any questions about that? It comes down to identifying, are these things polar, nonpolar? What's the strongest intermolecular force? Are they likely to mix? If they are similar, they will mix. If they're very different, they won't.